yesterday. It's really nothing new there. We're going to make sure we understand continuity, and we're going to know the definition and how to apply it. So I'm going to hit on that again so that maybe now your homework makes a little more sense. Finding points of discontinuity, right and left continuity. I talked a little bit about that yesterday. They're not going to ask you if a function's right continuous or left continuous. You're not even going to think about it. It's just going to be plain old continuity. Knowing which functions are always continuous. How do you compose continuous functions? What happens with those? And adding them, etc. And the intermediate value theorem. And I'm not going to give you the formal definition of the intermediate value theorem. I'm just going to say basically what it says. You use it. Everybody uses it all the time. Can you write down the 3 requirements for continuous functions? It's on the test. It is a test question. So how many of you should get it right? 100%. How many will get it right? 75. Okay, so can you write those down? Which part? Oh, these. Well, we're at 75% are going to get this question right. But all of you should get it right because I'm telling you it's a test question. I can't get any easier than that. To give you the question and the answer? Okay, are we ready? What's the first thing I would check to see if a function's continuous? I'm sorry, what? You're right, I think. What would you say? F of x or f of c must exist. That's a domain issue. Well, is this at a point? At a point C. That's a good question. So if I have this, at this point C, my function does not exist. So it's not continuous there. Does that make sense? It should all make sense. Forget memorizing. I mean, you have to memorize these little things. You have enough memorizing. But you can see it's not continuous. And then we can try to fix this. This is a removable discontinuity, and we can fix it. And last class says, well, how do you fix it? Well, I think it's Highway 19, has the bridge out. Do you think they're trying to fix the discontinuity? Absolutely. They're building a bridge, and I could see, having gone under the channel, through the channel under the bridge, I could see why they pulled that bridge out, because there are major cracks. It was just a matter of time before that bridge was going to collapse. That's what engineers have to do. Okay, so yes, you can fix those problems. Now, that's the first thing. You've got to have your function defined for all the points in the domain. Sometimes you'll have to exclude some values, but it'll be continuous everywhere. So, for instance, if I had f of x is equal to 1 over x, that's continuous everywhere, because we know what that looks like, right? Except at where? 0. Okay, so this is continuous everywhere except at that point. So you could check for continuity at every single point. Everything would be fine except for 0. Okay, that's the first thing. Now, what about, I'm going to erase this, the next one. So if I had a graph that looked like this, so we put a little jump in there, is the function defined for all values? Yes. So 1 is fine, but it's still not continuous because, how do you say that mathematically? There's a jump, but that's not math. Okay? Of f of x must exist. So the limit doesn't exist there. That's a problem. But even if the limit does exist, does the limit exist on this function right here? You're traveling down the road. Are you approaching the same place? Yeah. But it's sort of like 41. If you go down 41, you're approaching the same place from both sides, but there's a problem. There's another bridge. They're putting a bridge and underpass in so that the pedestrians can go under the highway rather than going over the highway. There's a break in the road. So what are they going to do? They're going to put in f of c. And they're going to fix that. So what's the last thing? Even though the limit exists here, f of c exists, it's down here, they have to be what? They have to be the same. So that's the last thing you have to have. So you have to be able to write these. just like I'm writing here. If you forget the x approaches c, it's wrong. Okay? So it's the limit as x approaches c of f of x. And if you think about it, it just makes sense. The limit has to exist and it has to be equal to the y value that's defined is equal to f of c. Some of you don't like the fact that we can fix things and we can define things, but it's the same as fixing this bridge, fixing 41, fixing the bridge Highway 19. We can fix those things. If there's the dams, if there's a leak in the dam, what are they going to do? They're going to fix it with plug the hole. But what? This is basically saying that these two lines have to be equal. So if you satisfy the third one, you satisfy the first and the second. So it's redundant, isn't it? Yes, but this is what they want. And when they say the limit must exist, they also want you to say the limit from the left of f of x equals the limit from the right. They're very particular about that. And see, already we can do some AP problems. Yeah. Oh, my box of prints, though. I did. I just brought it in here yesterday, I thought. Oh, maybe I didn't get it here. No. I'll get some, but not right now. Okay. Okay, guys? How do you find points of discontinuity? It's a domain question. Where are the problems? The problems is division by 0. So if you get a number divided by 0, what are you going to get? A vertical asymptote. I'm hitting on the key things. These are the things you need to know. So before the test, you're going to look over these notes. You need to look over all your notes. Can you do these problems again? Plus, we're going to give you a nice review packet. Monday and Tuesday. Yes, we always have two parts to the test, one without a partner, one with a partner. Now, that means the ones with the partner are usually harder. No, I don't believe we have any quizzes. I could give you a homework quiz. Don't remind me. Remember, I have 5 preps. I forget things. Yes, I let you choose your partners. Now, different teachers do different things. Okay? What's the other situation you get? You get 0 over 0, but that's going to be a what? Whole. You have to do work. This is fixable. It's called the removable discontinuity. We can fix that one. That's nice. When you get what? Too many wiggles, you can't fix it. It's just too many wiggles. The limit doesn't exist. If you have too many wiggles, then the limit doesn't exist, and so it violates Rule 2. Okay, so let's look at some problems. Ready? Let's look at the first one. And I didn't leave myself a lot of space, but that's okay. I can spray this. What about that one? Now, the first thing I look for is just division by 0. Where has this got a problem? When x minus 2 is 0 or x is equal to 2. And now, why is this discontinuous? Because f of 2 does not exist. That's it. I'm done. That wasn't hard. Is it an infinite discontinuity? How would I know? I'd have to put 2 in and see if I get a number divided by 0 or 0 over 0. In other words, you have to find the limit to see if it's what kind of discontinuity it is. Because if I substitute in 2, it's a very good question. I'm going to get 4 minus 2 minus 2 over 2 minus 2. I get 0 over 0. So this is a removable discontinuity. And remember, I told you that if you get 0 over 0 and these are polynomials, this will divide into that evenly. Doesn't work with the trig. But once I know that, I know one of the factors is x minus 2. Because this function behaves like whatever's left there. But I can do that easily, because how do you get x squared? X plus 1. Once you know one of them, the other factor is much easier to find. And since you know it was 0 over 0, it has to be the same. So this function looks like the line x plus 1. And if I were to graph it, we know what x plus 1 looks like. And know what? I'm going to be really lazy. I'm just going to do a table of values. When x is 0, y is 1. When x is 1, y is 2. It is a constant slope, except that when I get to x equals 2, I've got a little problem. By this definition, there's a hole there. Whoa. There it is. Now, if I wanted to fix it, I could. I could define my function and say that f of 2 is, what value does that have to be to fix that? I want the dot right there. So what does this end up being? 2 plus 1 is 3. I can define it that way. Just like your parents decided to name you whatever they named you. You could change your name. If you don't like your name, you can change your name. Okay, so it's just a definition. So I can fix anything I want. Well, I can't fix some of these. Let's look at the next one. Because we took this limit here. Right up here, I took that limit and I substituted 2 in. Because what's happening is as I get closer to 2, this is getting closer to 3. So I could take my classroom door and you could say, I want you to keep closing it halfway. Will it ever get closed? No. But what's the limiting value? What happens in the end? If I could close the door halfway an infinite number of times, it will eventually be closed. Make sense? So if I could get to 2 out at infinity, it will be 3, but I never get there. It's a limiting value. What's it getting close to? That's what's the function getting close to. That's it. So what about b? And I think I'm just going to write these down here because I don't have any space there. So b is f of x, and I apologize for the extra braces. That doesn't help because I didn't know how to use Word to get the one brace. Now this one, is this defined for all values? Yes. We will look at it graphically so you can see that it is. Okay? So f of 0 does exist. So I've got the first one exists. Then I check to see the limit. And let's look at the picture because it's clearer when I see the picture. Now you should know what this looks like. I don't like to be crooked. 1 over x squared looks like 1 over x, but since it's x squared, the negatives become positive, so it looks like this. And at 0, the y value is 1. What kind of discontinuity is that? I have vertical asymptotes, so it's an infinite discontinuity. Because, what's true about the limit? The limit does not exist. The limit as x approaches 0 of f of x, and because f of x is clearly defined up here, I can just write f of x. I don't have to recopy it, especially if you're complicated functions. This does not exist. You're right, it goes to infinity, but it still doesn't exist. A limit is a number, just like slope is a number. Okay, so the limit doesn't exist on that one because they defined it that way. How do I know what vertical asymptote? Because I know what the graph looks like. It's 1 divided by 0. What is the limit? As x approaches 0 from the right of 1 over x squared, this is 1 divided by 0 plus infinity. So we say it doesn't exist. Check. Yeah. Yes. Because that was just defined that way. It's a definition. If you are dealing with electricity, your voltage might be like this, a constant voltage. Turn the power off. Boom, it's down here. And then maybe there's a power surge, then it holds constant. I have to write piecewise functions to describe that. You can't do one single function because there's nothing exists. Now, if you saw this pattern all the time, you'd make up one. Yeah, yes, if you're talking about continuity, you want to say it just doesn't exist. Then you could do the plus infinity. Now, if it's negative infinity and you write positive infinity, you will get the point taken away. Better off to say it doesn't exist. You have to look at the context of the problem. You'll know when. Remember, we're just at the beginning. You will get lots of AP practice, and it's embedded throughout this course. Okay, so somebody defined this function, and they said, I want this to be defined everywhere, so I'll just give a value there, but it didn't fix the discontinuity. It's still not continuous because the limit doesn't exist. So same thing here with C. There's my function, and I'm going to take a picture of it, actually. We'll just put that on a new page. Let's do that one. Okay, it came out a little weird, but that's okay. Ignore that line in the middle. So first thing, what's f of 2 equal to? I don't put the lines there, but what's f of 2 equal to? 1. So somebody defined it that way. Whoever the author was, wasn't me. I stole the problem from someplace. Now, so the function does exist. The next thing to check is the limit. You have to actually find the limit as x approaches 2. You can't say it's not equal to f of 2 unless you know what it is. So, what's the first thing we do? Substitute in, right? Then we just do this one? Is that the same one? Yes. Actually, I did that one in a sense. So we found this limit. We factored it. And that was x minus 2, x plus 2, well, x plus 1, sorry, and x minus 2. So if you take the limit, this was 3, right? Okay, so why is this still discontinuous? I have it, the limit exists, the function exists, but the limit, I didn't plug the hole in the right place. As x approaches 2, does not equal f of 2. Okay? They're not the same. If they had put a 3 in here, we'd be fine. If they had done this, then you'd say it's continuous because it fixed the problem. The graph looks like x plus 1, and we actually did it. I'm going to go back. We did it over here, didn't I? It's this graph right here. So what happens is they're saying this is at 1. Did I fix the problem? No. Listen. No, it has to be up here at 3. We'll do another one. I got more. Okay, now for your favorite one, the greatest integer function that I found out that a number of you are having problems with. Well, first off, you have to know what it is. Now, is this going to be on the exam? No, but it helps us understand continuity. This is D. Because I know what's on the exam. It's not on the exam. There's an Acorn book. If you go onto the College Board website, you can see all the topics that are on the exam. Now, they might say step functions, but I know greatest integer is not in particular. Also, I'm part of a listserv, so we talk about what's on the exam, what's not on the exam. And I know for a fact this is not being tested on the exam. But what is tested is the continuity piece. So they could draw you any picture with it may not be a step function like this. This is not a step function, but we have a jump discontinuity. So you're still responsible for this. Well, this is nice because I get a nicely defined function that looks like steps. And so you have to know what it means. It's the greatest integer last class said what's an integer that's less than or equal to whatever's in there, to x. I want the biggest integer, but what's an integer? It's a whole number. So no fractions, no decimals, but I could have negative. Whole numbers and their opposites. The best definition I've ever found for an integer. So you're not going to have fractions. So if we were to do this one, 5.999, I want the biggest integer, whole number, that's smaller than that. That's 5. It's a rounding down function. Well, you aren't familiar with the greatest integer. You're familiar with the least integer. That's a rounding up function. That's what you use on your cell phones. If you talk for 2.5 minutes, what do you charge for? 3. What if it's 2 minutes and only a couple seconds? You're still charged for 3. That's a rounding up function. Ever parked in the parking lots downtown Minneapolis? If you go 5 minutes over your hour, they charge you for the next hour. Unless you're me, and I don't get charged for that. Depends on who's working the booth. I've gotten out of it. Okay. But if it's a machine, and more things are machines these days, so no, can't do that very well. It's simply a rounding down function. Do you remember what this looks like? It looks like steps. Now, you have to figure out where the open circles are. Where does it jump? I think the other one's going to be coming down, steps coming down. I don't know if it's on your calculator or not. But you don't have to know the other one at all. But you do. You deal with it. Anytime they say, or fraction thereof, you go to the airport and you park, you're 5 minutes too overdue, you're going to pay for the next hour. Like I said, everything's machines now, so it's not quite as easy. Okay, where's the problem? This is continuous. I actually have a continuous function. In here, it's continuous. But where's the problem? At the jump. And where does this jump? What kind of numbers are these? If this is 5.999, I stay down here at 5. But what happens when I go to 6? It jumps, doesn't it? So the jumps are, or the breaks in the graph, or however you want to say it, are what kind of numbers? Whole numbers, or they're integers. At the integers. Well, that's what kind it is, but what's the problem with it at the integer? The limits don't exist. That's right, excellent. As x approaches an integer of the greatest integer function, those don't exist. Inside, in the yellow part, that is continuous. If you pick a point in here, does the limit exist? Does the function exist? Are they the same? Yeah. No problems with that. It's just at the jump, and the jumps are at the integers. Here's a jump, and why? Because the limit from the left is 5, and the limit from the right is 6. So the limit doesn't exist. Remember, the limits have to be the same coming in from opposite sides. Sometimes my brain works like this, and I miss things. It's continuous everywhere except at the integers. Just the way I said it. Continuous. Greatest integer function is continuous at all x values except, you have to use word English, except when x is equal to an integer. Because the limits don't exist there. You might have to say the limit from the left is not equal to the limit from the right. Not exist at the integers. That would be your answer. I know. You are going to actually use some English on this exam. But try to keep it succinct. You know what that means? Short and to the point, concise. Succinct a little bit stronger. The reason is if you write too much and it's wrong, you get points taken away. Sometimes you get the points, but most of the time you get it taken away. It's a function. How do I know it's a function? Because it passes what test? Vertical line test. Okay, great question. It's not continuous. Where is, tangent function is continuous everywhere except at the vertical asymptotes. So it's exactly the same thing. This is continuous everywhere too, except at pi over 2 minus pi over 2, because the limits don't exist there. but it can be continuous everywhere in between. So the greatest integer function is continuous everywhere in between those jumps. Matter of fact, in particular, if I come from the right, that's actually equal to the value, isn't it? If I take the limit as x approaches, let's take 6 from the right side of my greatest integer function, that equals 6. What if I take the limit as x approaches 6 from the left side? What's that equal to? That's 5. This is f of 6. This is not f of 6. So this is not left continuous. So if you come in from this side, this value is getting close to has to equal the function there. It's not. It's dumped. So this is said to be right continuous. Now, they're probably not going to ask you any questions about right continuous. Although they might say a function is right continuous, it just means coming in from the right, everything's cool. Function exists, and whatever you think the limit's going to be is what the value of the function is. So now I just hit on some of those other things that are coming up. Okay, so let's try that one. Very similar. The same question, really. So take a look at that. Oh. Mrs. Richmond texted me, when's the homework quiz? Well, I don't know. Thursday sounds like a good plan. Having a homework quiz. Well, it has to be Thursday so I can get it corrected and back to you. Okay. What is f of negative 1? It's 6. Clearly that exists. So the next thing you check for is the limit. So I need to take the limit as x approaches negative 1 of this function, x squared minus 1 over x plus 1. First, what do we always do? Did I copy it wrong? Question? What's that equal to? What do I have to do? Substitute. So you get what? You get 0 over 0. That means there's a hole. This is a rational function. We know this is continuous everywhere except when this denominator is 0. So what we have to do is find this limit. I don't have to check left and right because we talked about it yesterday, we'll talk about it again today, these functions are always continuous except when the denominator is 0. So it's 0 at negative 1. So I just have to look at that limit. And so you get 0 over 0. I know it factors. So what's one of the factors in the numerator? X plus 1. Now it makes the factoring easier, although this one's not tough anyway. X minus 1. How many quadratics can be factored that are reasonable? Not too many. You've studied them all, and I've been doing all of them for 30-some years. Oh, probably 40. It's a long time. So if I factor fast, it's because it's already done in my head someplace. So we're going to cancel out the zeros because we don't care what happens at negative 1. It's not important. What's this value going to be? Negative 2. Is that equal to my value of my function? No. So let's look at the picture because I think that helps you to see it. This graph looks like y equals x minus 1 except at negative 1. So I'm going to put in 0. I get negative 1. I put in 1. I get 1 because I know it's a line. So it goes there and it comes down here. There's a hole in the graph. That's that one. And now we're going to fix the hole. We are the contractor, and we're going to fix it with at x equals negative 1 with y equals 6. Did I fix it correctly? No. Is it a function? Does it pass the vertical line test? Yeah, it does. Let me put it down here. Okay. But if I wanted it to be right, the next contractor comes in and says, we have to fix this. The bridge is going to fall down. So what are we going to do? We'll set our value at negative 1 not to be equal to 6, but what value should it be? This needs to be a what number? 0? No, what? negative 2. It happens. It happens when you're building things. There are no answers. So it says, explain why it's discontinuous, because the limit of my function as x approaches negative 1 of f of x does not equal f of negative 1. That's fine. Finally, the third one. The limits clearly exist, but you got to tell me what the limit is. The function clearly exists, but they're not the same. They are in this picture, but let me go back and put where it was. It's up here someplace. Question. Why is what? Okay, I talked about right continuous. How do you write that? And left continuous. Like I said, they're not going to probably say much about this on the exam, but the limit as x approaches some value from the right side, oh, it's a, of f of x has to equal f of a. So if I look at the square root function, which we did yesterday, my square root's doing this, and what's f of 0? That's 0. What's the limit as x approaches 0 from the right? Of f of x equals f of 0. So that's right continuous. If you're coming in from the right side, it's going to where you think it's going to go. Not left continuous, because the limit doesn't exist on the left side. So, but you would write it this way. The limit as x approaches a from the left of f of x has to equal f of a. We did the greatest integer function. Let's do it again. Let's look at this. Is this right or left continuous? This is right continuous. Because you end up getting the value of the function. The limiting value is this, and they're the same. Right continuous. What else? Yeah, I will. And then we're going to do the next thing. Then tomorrow, I don't think we have that much to do because I've done everything in this section. But you really need to try the homework so that you can ask me questions. I'm hopefully answering some of the questions. Yeah, hopefully we'll have the time to get to that. And I could do the intermediate value theorem tomorrow. Oh, that's what it was. Well, I have a lesson, but it's not much. I don't believe it's much. I'll have to look at it. I haven't looked at it. Okay, really quick theorem. If you have two functions that are continuous, f and g, they're both continuous, what do you think happens if you add them? Do you think it stays continuous? Sure, why not? What if you subtract them? What if you multiply them? So if you do operations with your functions that are continuous, the result's continuous. What if you multiply by a constant, some k times f, or k times g? So if you take a continuous function and multiply it by a number, do you think that changes it? No. And the last one is if you have f divided by g. This is continuous everywhere also. You can divide them, except where? Where's the problem? G is equal to 0. So you can operate on these. Very nice. But you do it automatically. I know x is continuous. I know 4 is continuous. You know x plus 4 is continuous. You do it without thinking, which is fine. Okay, we have this. We did this. I'll let you guys write those down on your own because we're running out of time and you have a homework question. We did this yesterday. We maybe come back and hit on it again tomorrow. But all these functions are continuous. The only thing that's kind of weird is this composition of continuous functions. This guy. And they're just saying if you compose continuous functions, you get another continuous function. Better than that, if I do this, if I want to limit, because that's kind of hard to read, I think, as x goes to some value of f of g of x, well, here's what you guys do. You just substitute in c and go on your way. And that's fine. That's what we all do. I'll give you an example where that's not going to work. But this is the same as this. You could take the limit operator and pull it inside that function. You will forget this theorem, the composite limit theorem. because you do it all the time without thinking. But I'm going to give you an example where it's not going to work, where it works, but you're not going to see it. What if I want the limit as x goes to 0 of e to the sine of x over x? What's the first thing we always do? We substitute. Well, you get confused too. We substitute, right? So that's e to the 0 over 0. But I can pull this limit operator inside the exponential function. This is the same as e to the limit. It just looks weird because it's up in the exponent, but I can do that. That's what that theorem says. So what's that? E to the what? We know that limit. 1. Normally, things aren't up in exponents, and so you automatically do it. So when you do the sine of x plus 1, and you take the limit as x goes to 0, for instance, you just put the 0 in there. But what you're really doing is this. It's the sine of the limit as x goes to 0 of x plus 1. That's really what you're doing. You'll just go ahead and put the 0 in here and say it's the sine of 1. The composite limit theorem is what says that you can do that. It's just a theorem allowing you to do that. So when you do this, you're really doing this. And that's 1, it's the sine of 1. You're pulling the limit inside there. We'll come in and hit on that over and over again as it comes up, because it will come up. Because I don't know how to do this limit up here if I don't pull this limit up into the exponent. How are you going to do that? Because you're going to get e to the 0 over 0. I just look at it and say, oh, when I look at this, that's going to be the limit, this particular limit, and I know it's 1, so I just do it. Quick question on homework. We'll do intermediate value theorem tomorrow. We do intermediate value theorem all the time. Somebody said they had a question on homework. Which one? Number 7? I'm sorry, I can't. Number 9, you mean? Just a second? I'll bet it's number 9. 15 and 16. What value should be assigned to make the extended function continue? Forget that extended function. You're fixing the whole. How about if we just say that? Sometimes the vocabulary in this book drives us nuts. What about this one? Where's the problem here? E to the x is continuous everywhere, but this is not. Because this is the composite limit theorem. What if x is 0? And that's e to the limit of 1 over x. What's the problem at 0? Well, you know what? We don't necessarily know because that's an exponential with a rational function. But I know because I graphed it in the other class, and there it is. That's what e to the 1 over x looks like. You just know it doesn't exist. The limit doesn't exist. If I can. That one? I want to take that picture, though. But I can do that in a second. So we will do the rest of this tomorrow. Intermediate value theorem is very important. It's day 2 on 2.3. So it's day, yes. It's day 7 and 8. Kind of. Let's go back and look at that picture again. This is one of those weird ones. There it is. From the right, it's a vertical asymptote. But from the left, 0 doesn't exist, but there's a limiting value. I'll bring in maybe a problem off the 2008 exam, if I remember it. It just doesn't exist. Because the limit from the left doesn't equal the limit from the right. That's all you need. Because that's what it's, so it's obviously discontinuous. There you go. Limit as x approaches 0 of f of x does not exist. Exponentials behave strangely when you do strange things to them. It just asks if it's continuous or not. It's not continuous at 0 because the limit doesn't exist. That's it. Yeah, let's not make it hard.